Direction ratios of a line. Welcome, everyone. Today, we are going to explore a fundamental concept in three-dimensional geometry, direction ratios of a line. Now, let's start by looking at what we already know. When we study two-dimensional geometry, describing the steepness or the slope of a line is quite straightforward. A single number, which we call the slope, is all you need to define how much the line tilts. However, as we move into the third dimension, things become a bit more complex. In a three-dimensional space, a single number is no longer enough to capture the orientation of a line. We need a more comprehensive way to describe the direction of a line in relation to all three axes, the x, the y, and the z axes. To solve this problem, we introduce a concept called direction ratios. As we move through the next few slides, you will see how these ratios allow us to precisely define a line's path in 3D space using vectors. Understanding direction ratios. Now that we've established that 2D geometry isn't enough to describe 3D space, let's look closer at how we define a line's orientation. In your previous math classes, you learned that a line in a 2D plane has a single, specific slope. However, once we move into three-dimensional space, a single number just isn't enough to capture the complexity of a line's tilt. Instead of a slope, we talk about the line having a direction. To make this concept mathematically workable, we can represent this direction using a vector. Think of a vector as an arrow pointing in a specific path. The key connection we need to make is this. If we have a line and we find a vector, let's call it vector b, that runs perfectly parallel to that line, then the individual components of that vector, its movement along the x, y, and z axes, are exactly what define the direction of our line. This sets the stage for our next slide, where we will see how these components actually become the direction ratios we've been talking about. From vector to direction ratios. Now that we understand that a line in 3D space is defined by its direction rather than a single slope, let's look at how we actually write this down mathematically. Suppose we have a vector, let's call it vector b, that is parallel to our line, which we'll label as line L since this vector is parallel to the line. It essentially points in the same direction as the line itself. To describe this direction precisely, we can express this vector in terms of our standard unit vectors, I hat, j hat, and k hat. We can write this as vector b equals a I hat plus b j hat plus c k hat. Now pay close attention to the numbers here. In this expression, the coefficients, which are the values a, b, and c, are what we call the direction ratios, or doctors, of the line L as we will see in the next slide. These three numbers are the key to constructing the vector itself. From direction ratios to vector. Now let's look at this concept from the opposite perspective. In the previous slide, we learned how to extract the direction ratios from a given vector. But what if the situation is reversed? Suppose you are working on a problem where you aren't given a vector, but you are simply told that the direction ratios of a line are a, b, and c in this case. You can immediately construct a vector that runs parallel to that line. You do this by simply using those ratios as your components. You would write the vector b as a times I hat, plus b times j hat, plus c times k hat. Essentially, you are turning those numerical ratios back into a directional vector. This ability to move back and forth between ratios and vectors is what we will use in the next slide to explore a real-world analogy involving a drone. Real-world analogy, the flight path of a drone. Now, to help you visualize what we've just discussed with vectors and coefficients, let's step away from the abstract math for a moment and look at a real-world analogy, the flight path of a drone. Imagine you have a drone sitting on a launch pad, ready to take off into 3D space. If you were working in a simple 2D plane, you could just give the drone a single slope or angle to follow. But as we learned in the previous slides, 3D space is more complex. You cannot simply give the drone a single slope value and expect it to know how to navigate the height and depth of the sky. Instead, you need to provide a specific set of instructions. You would tell the drone, move a units along the x-axis, B units along the y-axis and C units along the z-axis. This specific set of values, a B and C, is exactly what we call the direction ratios. They act as the navigational coordinates that tell the drone the exact orientation of its path through three-dimensional space. Now, here is a crucial point to remember before we move on to our numerical example. The direction itself doesn't change if you scale these numbers. If you told the drone to move 2 A units along the x-axis, 2 B units along the y-axis, and 2 C units along the z-axis, the drone would still be flying along the exact same path. The magnitude or the length of the instruction has changed, but the direction remains identical. This perfectly illustrates why direction ratios are proportional. Step-by-step example. Now that we have understood the theory and the drone analogy, let's put this into practice with a concrete example. Here, our task is to find the direction ratios of a line that is parallel to the vector v, which is equal to 3i minus 4j plus 5k. Once we have found those, we will also find a completely different set of direction ratios that represent the exact same line. Let's break this down into 3 simple steps. In step 1, we need to identify the coefficients of our unit vectors. Looking at our given vector, v, which is 3i minus 4j plus 5k, we simply pull out the numbers attached to each direction. So, our coefficient A equals 3, B equals negative 4, and C equals 5. Moving to step 2, stating the direction ratios is straightforward. We just group those coefficients together. Therefore, the direction ratios of our line are 3, negative 4, 5. Finally, in step 3, we want to find a proportional set of ratios. As we discussed in the previous slides, direction ratios are not predefined and are not unique. Any vector parallel to this line will have ratios that are proportional to our original set. To demonstrate this, we can multiply our original ratios by any constant. Let's call it k for this example. Let's choose k equals 2. When we multiply each of our original values by 2, we get a prime equals 6, b prime equals negative 8, and c prime equals 10. So, we can conclude that 6, negative 8, 10 is another perfectly valid set of direction ratios for this same line. As we move to the next slide, keep in mind that while these numbers look different, the direction remains identical. We will now look at some common pitfalls to avoid when working with these values. Common mistakes to avoid. First, a very common mistake is confusing direction ratios, or doctors, with direction cosines, which we call DCs. It is easy to mix them up because they both describe the direction of a line. However, there is a crucial mathematical difference. Direction cosines, which we denote as L, M, and N, are very specific. They represent the components of a unit vector, which means they must satisfy the condition L squared plus M squared plus N squared equals 1. Direction ratios, on the other hand, are much more flexible. They are simply the coefficients of B and C, and they can be any real numbers you like. They do not have to satisfy that unit length condition. Second, please be careful not to ignore the signs. In three-dimensional space, the direction is just as much about which way you are facing as it is about the magnitude. The positive or negative signs in your ratios are critical. For instance, a line with direction ratios of 1, 2, and 3 is pointing in a completely different direction than a line with direction ratios of negative 1, 2, and 3. A single sign change alters the entire orientation of the line in space. Finally, do not fall into the trap of assuming that a line has only one unique set of direction ratios. As we saw in our step-by-step example earlier, direction ratios are not unique. A single line can be represented by infinitely many sets of ratios. As long as you take your original ratios, B and C, and multiply them by any non-zero constant, let's call it k, the new set, Ka, Kb, and Kc, will represent the exact same direction. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. As you begin working through more complex 3D geometry problems, it is very easy to fall into a few specific traps, so please pay close attention to these 3 points. Keep these points in mind as you move on to our final summary of the key takeaways. Key takeaways. First, let's revisit the formal definition. Remember, direction ratios are simply the coefficients, which we call a b and c, found in a vector, b, expressed as a I hat plus b j hat plus c k hat, provided that this vector is parallel to our line. Essentially, they are the numbers that tell us how much to move along each axis. Next, let's look at the relationship between points and direction. While direction ratios tell us which way the line is pointing, they don't tell us where the line is located in space. To uniquely determine a specific line, you need two things: a fixed point that the line passes through, and these direction ratios to set the orientation. Third, keep the concept of proportionality in mind. As we saw in our drone analogy and our step-by-step example, direction ratios are not unique. If a b and c are direction ratios for a line, then any multiple, which we can write as k times a, k times b, and k times c, where k is any non-zero constant, will represent the exact same direction. Finally, remember the direct link to vector form. If you are given the direction ratios a, b, and c, you can immediately write down the parallel vector as b equals a I hat plus b j hat plus c k hat. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear before you move on to your practice problems. If you have reviewed these points and feel confident, you are ready to tackle the exercises. Great job today.